All right, hi folks, this is Larry Mussolino. I wanted to record a video for a STAT211. This is Module 2, the Chapter 4 homework. And this chapter has to do with correlation and scatter plots and finding best fit linear equations to a set of data points that are plotted on a graph like this that we call a scatter plot. All right, so let's take a look at this first example here. It says, disk drives are getting larger. Their capacity is often now in terabytes. And it says a search of prices found the accompanying data. So let's open up this data set and see what data was collected here. All right, so it looks like for different capacities, here's the price. And it makes sense. The higher the capacity, the more expensive the disk drive is, right? You know, if you go out and buy a disk drive, the more capacity, the more expensive the disk drive is going to be. Well, we'd like to form a plot. Notice here, these graphs are showing capacity on the x-axis and price on the y-axis. Now, this is a common way to set up these scatter plots, because the way you set up a scatter plot is you put the independent quantity on the x-axis and the dependent quantity on the y-axis. So in our example, we have to ask, does price depend on capacity, or does capacity depend on price? Well, of course, price depends on capacity. So that's why we're going to put price on the y-axis and capacity here on the x-axis. All right, well, for this scatter plot, we want to get StatCrunch to do it for us. So what I'm going to do is I'm going to go to this data set and copy it into StatCrunch. So here's a little copy icon, open in StatCrunch. All right, now we have the X data in the first column and the Y data in the second column. Remember, dependent quantity is always considered to be the Y variable. And so when you're working with correlation or regression, there's a command here in StatCrunch. It's going to be stat, then regression, and simple linear. The reason we say simple linear is we're going to be fitting a straight line fit to these points. We'll do more examples of that later. But for right now, let's go ahead and use this command so that we can generate the scatter plot. All right, so I'm going to come up here to the menu stat, regression, simple linear. And what StatCrunch wants me to do is identify what column has the X data, what column has the Y data. Well, remember, the Y data is the dependent quantity. That's price, because price depends on capacity. So the X is capacity. All right, that's all I'm going to do for right now. I'm going to click compute. And here's some information about the relationship between price and capacity. So one item I want to point out to you on this menu is a measurement called the correlation coefficient. And in this case, the number is 0.987. When a correlation coefficient is a positive number like this, that tells you the trend is going uphill. So this R number, if positive, means the correlation is going uphill. If this R number had been a negative number, that would be telling me the correlation is going downhill. Also, the closer this number is to 1, the stronger the correlation. So in our case, we have 0.987, which is a number very close to 1. This tells me this is a strong correlation. That means price correlates very well with capacity. All right, but I want to see the scatter plot. Well, there's actually 2 pages to this output. So if you click on this arrow here to go to the second page, we'll see the scatter plot. So let's do that. I'm going to go to the second page here. And here's the scatter plot. Now, I'm going to ignore this red line for right now, because what I'm trying to do is match up the blue dots with the my MATLAB choices. Let me see if I can get this side by side, perhaps, so that we can see the graph next to the data values. Okay, that's pretty good. All right, well, I'm noticing the trend or the pattern in these blue dots. Looks like it's starting here, and then it kind of goes up to this point up there. So definitely graph A is out and graph D is out. They don't match. But graph B and C are both pretty close to the pattern. So let me see if I can figure out which graphs really match. So let me try to see if there's a difference that I can identify in terms of a difference. Well, let's see here. I think the one difference is going to be maybe this point right here. Right, that point versus this point looks to be different. Well, if I'm noticing here, let's see, this scale is 4,500. So that means this scale is here is about maybe halfway. This is about 2,000, I'm going to say, just roughly. This point is way down here. This is more like 1,000. Well, I'm noticing our corresponding point on our graph is closer to 1,000. It's not up at 2,000. 2,000 would be up here somewhere. So our graph is matching graph B. All right, so I was able to generate the scatter plot in StatCrunch and do this comparison, and we're seeing it is matching up to graph B. All right, let's keep going to answer some more questions. It says, what about the direction of the association? Well, if you notice this, these points are heading uphill. That means it's a positive correlation or a positive association. So we're going to say here positive, generally positive. All right, let's go to the next question. It says, what can be said about the form of the relationship? Well, if you notice, what happens here is there seems to be this kind of curvature going on here. It's not exactly a straight line fit. There seems to be kind of a gentle curve. So we're going to say gently curved. All right, and then the last question I think says, what about the strength? Well, we're going to say relatively strong here because these points are fitting this pattern with that correlation coefficient of 0.988, I think it was. All right, it says here, does the scatter plot show any outliers? Well, there's really no outliers here because this point way out here is still fitting the pattern. If there was a point like way up here, this would be an outlier because this point is far away from the pattern. If there was a point way down here, this point would be an outlier because it's far away from the pattern of all the other points. So this point is not an outlier, but it is displaced from all the other points, right? All the other points are clustered down here, and then this one point is way up there. Well, I can figure out what point that is by going back to the data set. Let me go back to the data table and get that point. Well, it's this point down here at the very bottom, right? Goes from 32 all the way up to this 4,461, right? I mean, this is a very huge disk drive, 32 terabytes. All these others are in the range 0 to 12. So that's the one point that seems to be displaced from all the others. All right, let's see. I think that's it for this question. All right, let's go to another example. Yeah, let's go to another example where we have to do some more analysis using StatCrunch. All right, so it says here, data from a small bookstore are shown in this table. The manager wants to predict sales based on the number of salespeople working. So probably the more people working on the sales floor, the more sales because they're helping customers, pick out and purchase items. So let's open up this data set. And here's the data table. And it does look like, as I just scan over this data, it looks like as the number of salespeople working is going up, the sales is also increasing. All right, so that gives me a sense this is going to be a positive correlation, but let's open up this data set in StatCrunch so we could start doing some analysis. All right, so here it is. And again, we're going to consider sales to be the Y data because we believe sales depends on the number of salespeople we have out. All right, here's what they're going to ask us is find the slope, and then they're going to ask us find the intercept. So what is that about? Well, when we generate a scatter plot, let's go ahead and do that. So I'm going to go to stat, regression, simple linear. In this case, our X data is the number of salespeople working. The Y data is the actual sales. And I'm going to click compute. And let me take a look here at the correlation coefficient again, because that's an important number. And it looks like it's 0.952. That tells me it's a positive correlation. So I'm expecting the scatter plot to show points that are going uphill. And I also can see it's a strong correlation because this number 0.952 is a number close to 1. The closer R is to 1, the stronger the correlation. The closer R is to the number 0, the weaker the correlation. All right, but I want to see the scatter plot. So I'm going to click here where I can go to the next screen. So let me do that. All right, and here's the scatter plot. And I could see this is a pretty good fit because these blue dots are pretty well aligned with the straight line fit. All right, well, what we'd like to know now is what is the equation of this red line? We call this the equation of best fit or the regression equation. Well, if you remember back in algebra, for a straight line, you wrote the equation as y equals mx plus b. M was the slope of the line, and and b was the y-intercept of the line. Remember, the y-intercept was where the graph crossed the y-axis, and the slope was a number that told you how steep the line is. All right, well, I'd like to know what is the slope and what is the y-intercept. Well, let me go back to the first screen because StatCrunch is going to give you these two numbers. Let me go back here. And if you notice right here in this line, StatCrunch is giving you the slope and the y-intercept. So in our example, we're really thinking of sales as y. So I'm going to write this as y. And we're thinking of the number of salespeople as x. And so the number in front of x is 0.853. And this number in front here is 9.231. Well, if you compare this, this looks like b plus mx. So our slope here is 0.853. And our y-intercept is this b number, 9.231. Now, in our textbook, we call the slope b sub 1. So this number here is b sub 1. So the slope for us is 0.853. So here it is. And then it says, what does this slope, what does b1 mean in this context? Well, 0.853 is multiplying x. X is the number of salespeople you have out on the floor. So for each additional salesperson working, you're going to get an additional $853 in sales. The reason is the sales number is in 1,000. So when I have 0.853 here, it really means 0.853 times 1,000 in sales. So the slope is really anytime you change x by 1, the slope is how much y changes. So what this is telling me is if I add an additional salesperson out on the sales floor, I expect sales to go up by $853. All right, let's come down here. It says find the intercept b sub 0. Again, our textbook calls the y-intercept b sub 0. So for us, b sub 0 is going to be 9.231. All right, well, they want to know what does that mean in context. Let me scroll down here. Well, if you look at this equation, what if x was 0? Right here was the equation. We had y equals 9.231 plus 0.853x. If x equals 0, then y, if x is 0, this expression would go away, and y would equal 9.231. So really 9.231 is the expected amount of sales when you have 0 salespeople working. But really that doesn't make any sense. It's not meaningful because you would never have 0 salespeople working. So it really doesn't make sense in the context of this problem to let x equal 0. That's what the y-intercept is. The y-intercept is the y value when x equals 0. Sometimes it makes sense to let x equal 0. Sometimes it doesn't make sense to let x equal 0. Here, since x represents the number of salespeople working, it would not make sense. Well, here it says, write the equation that predicts sales from number of salespeople working. Well, this is exactly the equation we have here, because this is exactly the equation that StatCrunch gave us. We rounded the numbers, of course, but that was the equation. All right, and this lets us predict sales for any number of salespeople. Let's go to the next question here. The next question says, if you have 18 people working on the sales floor, what sales do you expect? Well, with this equation, right, y equals 9.231 plus 0.853x. If x equals 18, I'm just going to plug in an x equal 18 then. So this would be 9.231 plus 0.853 times 18. I can just work this out on my calculator. And if you do, you get the answer 24,581. So if you have 18 people out on the sales floor, you expect your sales to be a little over $24,000. Now, it turns out StatCrunch does this calculation for you, even though this calculation is not that difficult to do. StatCrunch does it for you. Let me go back to the previous screen, and I'll show you how you can do it. So I'm going to come back here to, this was the screen we were just working with. And notice right here, it says prediction of y. So if you go to this x value and type in a number, for us it's 18, and click compute, and I'm going to scroll down a little bit here. You could see it says if x is 18, the predicted value of y is 24.581. But remember, sales were in thousands of dollars, so I'd have to multiply this by 1,000. So sales would be 24,581. All right. Well, here's the last question. If sales are actually 24,000, what is the value of the residual? All right. Well, for this, we have to know, what do they mean when they say residual? Well, in our example, we just predicted that if you have 18 salespeople on the sales floor, your sales would be 24,581. Remember, that's a prediction. What if we actually did put 18 people out there? Maybe the sales actually turn out to be $24,000. Remember, this is just a prediction. It's not an actual observed value. It's just a guess. Well, to figure out the residual, what you do is you take the actual and subtract the predicted. That's the definition of a residual. So for us, the actual was 24,000. And our prediction was 24,581. So this turns out to be negative 581. A residual can be positive, it can be negative. It all depends on the specific example you're working on. All right, it says, have the sales been overestimated or underestimated? Well, our prediction was the sales are going to be 24,581. They actually came in at 24,000, so they came in lower. That means our estimate was too high. It was an overestimate. Our prediction was an overestimate. All right, so StatCrunch came up with this equation of the best fit line through the data points. And remember, that equation is the equation of this straight line that shows up on the scatter plot. So this red line is governed by this equation that we just came up with. All right, folks, let me do one more example. All right, so here they're going to give me a data table on a bookstore. So this is the same kind of data we were just looking at, number of salespeople working and the corresponding sales in 1,000. So I'm going to open this up in StatCrunch so we can start looking at it. All right, so here's the data set opened up in StatCrunch. I'm going to go ahead and do stat regression simple linear again. The X variable is number of salespeople working. Y variable is sales in 1,000. And I'm just going to click compute. And if I come over here, I'm noticing there's that correlation coefficient R. Again, in this case, it's 0.981. But right below it, there's another value called RSQ. That stands for R squared. Sometimes we write it as just an exponent 2 like this. In our case, the R squared number is 0.9625. Now, usually you write this as a percentage. So notice the question is, what is the value of R squared? Well, we're getting that right here from StatCrunch, but I'm noticing StatCrunch, my math lab wants it entered in a percentage form. I know that because I can see the percentage symbol there. So I'm going to change this to percentage. So it's just 96.25%. All right, so that's R squared, the number, but what does it really mean? Well, we call this the coefficient of determination. That's the fancy name for it. It's R squared. Sometimes you see it written with a lowercase r too. And what this does is it tells you, R squared tells you the percentage of variation in the Y value. In our case, that's going to be sales, based on the variation in the X value. That is number of salespeople working. Really, this is telling you what percentage of the variation is accounted for by this linear equation, this linear model. You want R squared to be a number close to 100%. Closer to 100%, the better your model. So our answer is going to be answer B here. 96% of the variance in sales is accounted for by the regression model for sales on number of salespeople working. So R squared is always the variation in Y. This first answer is wrong because it's talking about the variation in X. R squared measures the variation in Y that's accounted for by the regression model. All right, folks, hope this is helpful as you're working in this module 4 homework.